are going to discuss nucleophilic substitution reactions.
Organic reactions are chemical reactions involving organic compounds. The basic organic reactions are addition, elimination, substitution, and rearrangement reactions. In organic synthesis, organic reactions are used in the formation of new organic molecules. The production of many man-made chemicals such as drugs, plastics, food additives, fabrics depends on organic reactions. We are mainly focusing on substitution reactions. Substitution reactions are reactions in which an atom or group of atoms in a molecule is replaced or substituted by different atoms or group of atoms. For example, the reaction between methane and chlorine. In this reaction, hydrogen is replaced by chlorine. Substitution reactions can be further divided into two types: electrophilic substitution and nucleophilic substitution. The substituting species may be either a nucleophile or an electrophile. Before going into the details, I would like to introduce the concept of electrophiles and nucleophiles. Electrophiles are electron-loving species. A reagent which can accept an electron pair in a reaction is called an electrophile. They are electron-deficient species. They may be positive ions including carbonium ions or neutral molecules with electron-deficient centers. It can be represented as E+. Some common examples are H+, NO2+, sulfur trioxide, BF3, aluminium chloride, etc. Nucleophiles. They are nucleus-loving species. A reagent which can donate an electron pair in a reaction is called nucleophile. It can be represented as Nu-. Some common examples are water, ammonia, OH-, etc. Coming to nucleophilic substitution reactions. In the year 1935, Hughes and Ingold studied nucleophilic substitution reactions of alkyl halides and related compounds. They proposed that there were two main mechanisms at work, both of them competing with each other. The two main mechanisms are the SN1 mechanism and SN2 mechanism. Here, S stands for chemical substitution, N stands for nucleophilic, and the number represents the kinetic order of reaction. That is, SN1 is substitution nucleophilic unimolecular reaction and SN2 is substitution nucleophilic bimolecular reaction. Move on to substitution nucleophilic unimolecular reactions. The hydrolysis reaction of tertiary butyl bromide with aqueous alkali to form tertiary butyl alcohol is a well-known example of SN1 reaction. The rate of this reaction is proportional to the concentration of the halide. So, it is a unimolecular reaction. Let us discuss the mechanism of SN1 reaction. The hydrolysis takes place in two steps. In the first step, the tertiary butyl bromide slowly ionizes to form tertiary butyl carbocation. Then it is stabilized by the delocalization of positive charge by the electron donating inductive effect of the three methyl groups and by the hyperconjugative effect due to 9 alpha hydrogen atoms. In the second step, the tertiary butyl carbocation rapidly combines with the nucleophile, here it is OH-, to form tertiary butyl alcohol. Carbocation is the intermediate in this reaction and it is sp2 hybridized. We know that this is a flat molecule. Now there is equal chance for the attack of the nucleophile from either side of the carbocation. So an optically active halide should give a racemic alcohol. Let us move on to SN2 reactions. The well-known example of SN2 reaction is the hydrolysis of ethyl bromide with aqueous alkali to form ethyl alcohol. Here the rate of the reaction is directly proportional to the product of concentrations of the halide and the nucleophile. Therefore, it is a bimolecular reaction. Coming to the mechanism of SN2 reaction, this hydrolysis reaction takes place in one step. The nucleophile, here it is the OH minus ion, attacks ethyl bromide from the side opposite to the bromine atom to form an intermediate transition state. In the formation of the transition state, the carbon atom carrying the bromine changes from the sp3 hybridized state to sp2 state. Here the bromine atom and the nucleophile are attached to the two lobes of the unhybridized p orbital to form half bonds. Then the bromine is expelled and the carbon atom changes back to the sp3 hybridized state to form the alcohol. Since the nucleophile attacks the carbon from the side opposite to the bromine atom, there should be inversion of configuration. So, optically active alkyl halides give optically active alcohols with opposite configuration. The salient differences between the two mechanisms are listed in this table. This cartoon represents the summary of SN1 and SN2 reactions.
Hope you all understand this topic very well. Thank you for your kind attention.